Okay, hello everyone. Can you please confirm if you can see my slides or not?
Yes.
Okay, thank you. Okay, so as you remember, our last lecture was basically only introduction to the course. Uh, give me just 1 minute. Okay, sorry for the interruption. Let me just resume the recording again. So okay. So, as you remember, our last lecture was basically only introduction to the course. Most of the information was about how the course will be conducted, uh, with last couple of slides only about the pin mapping between the Arduino Uno board and the microcontroller pins themselves. So that was like what we did in the last lecture. But today we are going to start with the first topic of the course, which is basically about how we can encode the numbers and how can we represent them in a computer system or in any digital system. So before I start with the today's lecture, are there any questions related to the previous lecture or any difficulties with the previous lecture and anything you want to ask? Okay, if not, so first, I just want to make it a disclaimer that I haven't prepared these slides. I have borrowed these slides from Dr. Sean Cooper, who has been teaching this course for like multiple times for many previous offerings. So I may make some changes here and there, but the majority of the content will be same. Okay, so this is basically the microcontroller which we are going to study in our this course. It is from the Atmel, but now they have. I mean, Atmel was bought by another company named as Microchip, but they kept the name of the microcontroller as it is. They haven't changed it because it is already in. It is already widely used. Uh, and it is named as AVR, where AVR is just abbreviation for the name of the people who actually designed this microcontroller or processor. So I'm not going to pronounce their names because I know I will pronounce their names in the wrong way, but you can see the name of the designers on the screen. So the designers were like two students from Norwegian Institute of Technology. And you can consider that this chip is basically a miniature computer. If you remember from previous lecture, I shared with you guys a picture where we had like block level diagram of a microcontroller. So within the single chip you have multiple components, like you have CPU, you have a memory chip for both holding data and holding the code. You have also IO unit to interface with the peripherals. You have on-chip component for analog to digital conversion and so on, right? So everything is contained in a single chip. So you can consider it just like as a miniature computer. The AVR microcontroller, which we are going to study, it is basically a Harvard architecture. What does it mean to be a Harvard architecture? We will discuss it not today, but in the next lecture, hopefully. But the basic idea is that the Harvard architecture, basically what does it do is that it maintains the separate data memory and separate code memory. So it doesn't have a single memory chip to hold both data and the code. it actually has two separate chips, and those chips are connected with the CPU using separate buses. So that is the basic idea of Harvard architecture. But why we do so, we will talk about that in the upcoming lecture. Okay. But at this time, it is sufficient for you to know that Harvard architecture is basically an approach to improve the performance by maintaining the separate code and data memory. Uh, and this microcontroller is an 8-bit RISC single chip. So what does it mean, 8-bit RISC? So 8-bit basically means that all this microcontroller has internal registers, and those registers are basically used to hold the data. So whenever a CPU, let's say, performs an addition operation, so the operands on which the addition operation is performed, they are read from the registers. So registers are like data holders, and those registers are 8-bit in size. Uh, so that's why we name it as an 8-bit architecture. And RISC architecture, RISC here stands for Reduced Instruction Set Computer. Again, we will talk about it in the upcoming lectures, but uh, the basic idea of the RISC is like it is a design paradigm where the main idea is that the hardware supports only a limited set of instructions, and hardware is not capable to perform. Actually, hardware is not able to support complex instruction. What does it mean when I say simple instruction and complex instruction? So let's say uh, add is a simple instruction where I'm just adding two numbers, right? Uh, and let's say I have another instruction, for example, multiply. Now, designing multiplier, if the multiplication operation is supported in hardware, then it can be performed quickly as compared to the case where hardware does not support the multiplication operation and we use repeated add operations to perform the multiplication. Like for example, if I say 2 times 3, so 2 times 3 is basically I am just adding 3 two times, right? 3 plus 3 is 6. Similarly, 2 times 3 is also 6, right? So either I can use a multiplier to perform 2 times 3, or I can use the adder to add the number 3 two times, right? So 3 plus 3 is also 6. So, but designing multiplier is more complex. But on the other hand, the advantage is that if uh, my hardware supports the multiplication operation, it will be performed quickly. Quickly mean it will take less time. On the other hand, if I use repeated addition to perform a multiplication job, then yes, I will be able to do it, but it will take longer, right? So anyway, we will talk about RISC, reduced instruction set computer, and CISC, complex instruction set computer, in an upcoming lecture. But for now, just an introduction. It is enough for you guys to know that AVR microcontroller, which we are going to study, is a Harvard architecture. It is a 8-bit microcontroller, and it is a RISC computer, a RISC microcontroller. Okay. And by the way, if you have any question or confusion at any time, just send me a text message, text in the chat box, and I will try to respond. Okay. Okay, so here on the screen, when you see this chip, it has written on it at Mega 328P. So actually, that is not, random. The name is not selected random. So 32 here basically it represents some information. So 32 here basically mean that it has 32 kilobyte of code memory, or basically which mean that the maximum size of the program which we can run on this microcontroller is 32 kilobyte, right? And 8 means that it is an 8-bit processor, and P basically talks about it power consumption. So P stands for pico, which means that it consumes very low power. Okay. uh, okay, so what we are going to discuss in rest of the lecture today, we will be covering okay, we will be covering number systems, and then how we can convert a number from one system to another system, and also how we can represent negative numbers in binary form. And at the end of the slides, we will talk about ASCII code, right? So we are all familiar with the decimal system, right? So in the decimal system, we have basically 10 different symbols or 10 different figures, right? So from 0 to 9. And if we want to count beyond 9, then what we do, we start using the same symbols in a repeated fashion. So after 9, what we do is that we go back, we use 1 and in the decimal place, and then in the unit place we start putting the starting repeating from 0 again, like 1 0 1 1 1 2 and so on, right? So it becomes 10 11 12 13 and so on, right? But the basic idea is that in total we have only 10 different symbols. Now if we talk about hexadecimal system, so in hexadecimal system we have uh, 16 different digits. So these did from 0 to 9, these digits are same as in the decimal system, but then after that we have six more figures or digits, which are like A, B, C, D, E, or F. So the A is basically equivalent of 10 in decimal system, B is equivalent of 11, C equivalent of 12, D 13, E 14, and F is 15. Okay. So we have 16 distinct figures or symbols in the hexadecimal system. Now, if we talk about octal system, so hexadecimal system is, by the way, also known as base 16, and decimal, as you know, is like base 10. So octal system is like where we have in total 8 different symbols, like from 0 to 7. And when we reach the highest symbol, which is 7, then we do the exactly the same thing what we did in the decimal, like we uh, put the 1 in the decimal place, and then we start with 0 again. So 1 0 1 1 1 2 1 3 1 4 1 5 1 6 1 7 and so on, right? So basically what we are saying here is that 1 7 in octal is same as 15 in decimal or F in hexadecimal, right? So now, then in octal system, the base is 8. So now at we come to the binary system, and here the base is 2. So which basically mean we have only two systems, only two figures or two symbols, 0 and 1. So after like 0 and 1, we if we want to beyond count beyond 1, then we have to again repeat the symbols. So we use 1 0 and then 1 1, which is 3 in decimal. So at 1 1 we are again at the like highest value because both symbols have taken their maximum value. So we need to move to the next position, put 1 there, and then start again from like counting from 0 0. So it again becomes 1 0 0, and then for 5 it is 1 0 1, and 6 it is 0 1 1 0, and 7 is triple one, and so on, right? Any questions at this point? Any confusion? Okay, so if you have any questions, please let me know. Okay. Uh, Let me just check if I can draw. Yeah, okay. Okay, so how we represent these numbers, how we can represent the numbers using different systems when we are, let's say, writing the assembly uh, code or an assembly program for AVR microcontroller, right? So, like, let's say uh, I want to represent a number in binary. So if I want to do that in my code, then I need to specify the base of the number. So for example, if I want to represent in binary, so I must put a leading 0B in front of the number. So in this example, as you can see, here I'm telling the um, microcontroller that treat this number as a binary number, not as a decimal number, not as a hexadecimal number, because you know if you can, the value of this number in decimal will be different as compared to the binary, right? We will talk about how we can convert from decimal to binary or to other systems. But for the time being, we just need to, we just want to know how we can specify a number in the assembly program using different, using different numbering systems, right? And if you want to specify a number in octal system, then you need to put a leading 0 in front of it. So for example, if you write 076, then in AVR assembly, you are saying that 76 is the number 076 is a number specified in octal system, not in the decimal system. So it is not equal to, it is not equal to, it is not equal to 76 in decimal, right? Yeah. Let me check if I can use. Okay, so uh, when you want to specify a number in the decimal system in your in the assembly language, you write the number as it is. There is nothing you need to put in front of it. No zero, no nothing, no zero D, nothing. Okay. So, for example, if you write 62, it's mean it is number in in the decimal system. And when it comes to the hexadecimal, you need to put a leading 0x in front of it. So it can be like small x or capital X, doesn't matter, but you can put 0x, like for example, here as shown in the example 0x4f2a. So you are telling the assembler or you are basically saying that treat this number as a hexadecimal number. Okay. Okay, now how can we convert to decimal numbers? Like for example, if let's say you have a number in the binary system, how can you convert it in the decimal number, or from how you can convert from hexadecimal system to the decimal, or from octal to the decimal? So let's try this, but first starting with conversion from decimal to decimal. So what does it mean? Let's say you have 25 in decimal system. So how we can convert it? Basically, what we do is that for every digit starting from the right, we just simply multiply it with the increasing power of 10. Like for example, we multiply 5 with 10 raised power 0, we multiply 2 with 10 raised power 1, but then we add their product. So here you can see, why can't I? Okay, let me try. Yeah, so here, for example, I can simply add uh, the product here. Okay, so it becomes equal to 25. So exactly same approach is also used whenever you want to basically convert numbers which are written in in other systems, for example, binary, and you want to convert them into the decimal numbers. So here is an example of how we can convert a number which is specified in binary to equivalent decimal value. So let's say the number we have is 1011, and 2, basically here it is specifying that this is the base of the number is 2, just like here we specified that the base of the number is 10, right? So how we convert it to the decimal? Exactly same thing. What you do is that you multiply each symbol with increasing value of power of 2. So here you can see the power of 2 is 0, then 1, 2, and 3, so on. And then you are simply multiplying it with the corresponding figure or symbol. Like here, 1 times 2, 0, 1 times 2, 1, 0 times 2, 0 times 2 square, and 1 times 2 cube. So I'm just multiplying this. And then you are summing all the products here. So this will give you the value equivalent of 11 in decimal system. Okay. Any questions? No? Okay. So the now let's move to how we can convert a number specified in octal system to equivalent decimal value. Again, exactly same thing. You have a number 76, and this time base is 8. So what you do is that you simply multiply with the increasing power of 8, like 8 power 0, 8 power 1. You multiply with the corresponding symbols. Like the first symbol is multiplied with 8 power 0, second one with 8 power 1, and then you take the sum of the products. And this will give you the value of 62 in decimal system. Again, decimal to decimal, it is exactly the same thing, only the value is different, as we have seen in the first example. So you multiply with 10 raised power 0 and 10 raised power 1. You multiply the 6, which is the first number, sorry, the first digit with 10 raised power 0, and 7, which is second digit with 10 raised power 1. And then you get the sum. Okay, what about hexadecimal to decimal? I guess by this time you have already got the idea how things are working here, right? So when you want to convert from hexadecimal to decimal, the base is 16. So what you do is that you use the increasing power of the base, which is 16 power 0, 16 power 1, and you multiply with the corresponding. digits of the number, like 5 and 10, and then you get the sum, so you will get 165. Okay, so here in this slide, we have talked about how we can convert from other systems to the decimal numbers, like from binary, octal, or hexadecimal to decimal numbers. Now let's talk about how we can convert a decimal number to the binary numbers, right? So just first keep in mind, just as I said earlier, that in decimal number system we have 10 figures starting from 0 to 9, and in the binary we have only two, which is 0 and 1, right? So to convert a number from decimal system to its equivalent number in the binary system, we can do the repeated division. What does it mean? So let's try to understand using an example. Let's try to convert 25 to the equivalent binary number, right? 25 we have in decimal systems, right? So what you do is you divide 25 by 2 and you write the quotient and remainder. So if you divide 25 by 2, your quotient will be 12, your remainder will be 1. So what you do is that you keep dividing the quotient until you reach a point where quotient is 0. So what does it mean? So here what you do is you divide 12 by 2 again, and this time you get the quotient 6 and remainder is 0. Is quotient 0? No. So we can continue the dividing process. So we divide 6 again by 2, so you get the 3. You divide 3 again, so quotient is 3 and remainder is 0. So you divide then 3 by again by 2, so you get this time quotient at 1 and remainder of also 1. And now you divide 1 by 2, so this time our quotient is 0 and remainder is 1. So when we reach a point where quotient is 0, we stop. And then what we do is that we write all the remainder values from from downside to upward direction. So it becomes 1 1 0 0 1. So the bit at the end is basically the most significant bit in the binary number, and the bit at the top is basically the least significant bit in the binary number. So in this way we get the equivalent binary number for 25 as 11001. Any questions here? No? Okay. If no questions, then I want you to do this exercise. Okay, here it says it's a group exercise, but I think I guess most of you are attending the lecture in an individual capacity, so you are not in the classroom. So try to do this exercise on your own and convert the number 352 from decimal system to binary equivalent value or equivalent number. And you have 3 minutes to do that. Let me know uh, when you are done. Yeah, so the answer is 10110 and then all zeros. So please check if you have the same answer or not. And if not, then I'm going to share the solution here. So I can walk you through the solution and then you can confirm or you can see where did you make the mistake. So again, we are basically doing the same thing. We have 352. We are doing the repeated division. So first division, we have 176 as quotient and remainder is 0. Then we keep again do the same thing. So the remainder is 88. Sorry, quotient is 88, remainder is 0. And then quotient is 44 and 0 because we know these are the even numbers, right? So for even numbers, when you divide by 2, you will always get a remainder of 0. So 22 and 11. So until this point, our remainder is 0. And then if we divide 11 by 2, so this time we have a quotient of 5, remainder 1. Next time we have quotient of 2, remainder 1. And next time we have quotient of 1 and remainder 0. And then we finally reach at the end point where we have quotient of 0. So if I now write these numbers uh, from the bottom to the top position, then you will come across like the number you will get will be 10110 and then all zeros are 400. Okay, so again, if any questions, please let me know. Okay, now how can we convert? We basically talked in the previous slide how we converting a decimal number into binary. So now how can we convert a binary to decimal? So uh, let's first again go back to the same approach where we first look at how we can convert a decimal number to decimal number. So I have already explained how you can do that. So if you have a decimal number of like 740,683 in base 10, so converting it into the decimal is the same thing that you multiply all the you multiply the figures with the increasing symbols with the increasing power of 10. So 10 power 0, 1, 2, 3, 4, and here on the you multiply with 3, 8, 6, 0, 4, 7, and you will get some products, right? And then at the end you get the here you do the summation of all those product values. So will this will basically be the same number, right? So we are converting from decimal to decimal, right? Now how we can convert from binary to decimal? And we know in binary we have base of 2. So let's say we have this number 110101. So again, exactly same approach again, that you multiply the consecutive symbols or figures with the increasing power of 2, because this time the base is 2, not 10, right? So you have 2 raised power 0 up to 2 raised power 5, and then you multiply each one of them with the corresponding bit position value in the corresponding bit value, like 1 and then 0, then 1, right, starting from the right, not from the left, right? Starting from right, because right is the least significant. Okay, so 1 0 1 0 1 1 and so on, right? And then you get the product, and then after getting the product, what you could do is that you will simply the product in decimal, and what you do is that you simply sum that all of those products. So like 1 2 4 8 16 32, when you sum all of them you will get 53. Okay, so 53 is the decimal value equal to the 110101 in binary system. Okay, so here we have seen that how we can convert the binary number to the decimal number. So this is basically known as conversion by weights, right? So if, again, let's have a look at another example. What we are doing basically here is that we are multiplying each binary digit or each binary symbol with with its weight, and the weights are increasing from right to left, right? So let's say we want to convert the number 11001, which is in binary form, to the equivalent decimal value. So we simply first write the number, which is, if I read from most significant to the least significant, so it is 11001, right? So I simply first put the weights. So I know what are the weights, because here, 2 raised power 0 is 1, 2 raised power 1 is 2, 2 raised power 2 is 4, and so on. So 1, 2, 4, 8, 16, 32. So I simply first put the weights starting from the right. So it is like 1, 2, 4, 8, and 16, right? So in all the locations where I have the corresponding binary digits as 0, I simply ignore them. I can simply ignore them, and for the remaining where I have the binary digit value of 1, I can add those weights. So basically what I'm saying is that I can add 16 to 8 and to 1, and I can ignore these ones because here the binary digit or the binary symbol is 0. So when I do so, I will come across 16 plus 8 plus 1, which is equal to 25, right? Any questions? Basically, it is the same thing. The only thing is that instead of multiplying with the increasing power of 2, we simply know the weights because 2 raised power 0 is 1, 2 raised power 1 is 2, and so on, right? Now, how can we convert uh, a decimal number to the binary form using weights? So again, let's say we want to convert 39 to binary, right? And let's say I write first few weights in the weights in the decimal sorry, in the binary system. 1 2 4 8 16 32. Definitely when you continue it will be like 64 128 256 and so forth, right? So how can I convert? So basically what you can do is like, okay, I want to convert number 9, which what weight I have, which is power of 2 and is closest to 39. So after 32 I have 64. Now 64 is greater. If I write here just to like explain, so after 32 I will have 64. Now 64 is greater than 39. So I need to look for a weight which is not greater than 39 but is closest to the 39, which so it means 32, right? So if I now subtract 39 from 32, I will have what is left behind? 7, right? So what weight now I have which is closest to 7 but not greater than 7? So it is 4, right? So now if I subtract 4 from 7, so I'm left with 3. Now what weight I have which is closest to 3 but not greater than 3? So it is 2. Now if I subtract 2 from 3, I'm left with 1. So the next weight I can pick is 1, right? And then if that is the case, so it's mean I will, for all the weights which I have picked, what I can do is I can write 1 for that. So for here, I'm writing 1 for 32 because I selected 32. I'm writing 0 for 16 and 8 because I didn't pick them. And for 4, I am selecting 1, I'm putting 1 again. For 2, I'm putting 1. And for 1, I'm putting 1, right? So my binary will be 1001111. To be honest, this is like a bit confusing and complex approach. I mean, I would never do that. I just want, I mean, this is only included because this is an alternative way to do that. But to me, it is more complex. I would prefer like if I want to convert from decimal to the binary, I can do repeated division, right? Repeatedly, I can divide with 2 and then I can simply list the remainders from top to bottom. No, sorry, from bottom to top. Okay. Any questions? Okay, now how can we convert between binary and hexadecimal? We have talked about conversion from binary to decimal and decimal to binary. What about conversion between binary and hexadecimal? Again, remember that in hexadecimal, we have 16 digits starting from 0 and going up to F, right? And in decimal, in binary, as you know, we have only 2 digits. Now let's say we have the binary number, this binary number, and we want to convert it in hex. So if you want to it is as compared to conversion from binary to decimal, this is kind of straightforward. So if you want to convert it into hex, what you do is that you uh, group the binary digits or the bits in group of 4. Like you have one group of 4 bits here, then you have next group of 4 bits here, and then you have 1 bit left here, right? And then you can convert these groups into the uh, hexadecimal. So 101 is basically 5, right? You can convert it into decimal if you want. So 101 is 5. How I know? Because here that I have 2 raised power 0, which is 1, but next bit is 0, I ignore it. So the weight is 1, then 2 weight is ignored, then 4 weight is counted. So 4 plus 1 is 5, right? So here I have 4 and here I have weight of 1. 4 plus 1 is 5, right? So I simply write 5 here. Then for the next group of 4 bits, I also do the same thing. So if I convert this into decimal, so it will become 15. You can do it on your own if you want, just to confirm. So it will become 15, right? These 4 bits. And 15 in hexadecimal is F, right? So I write F here. I simply replace that group of 4 bits with F. And then I'm left with 1. So 1 in binary is also 1 in same 1 as in hexadecimal or in decimal. So it doesn't matter. So 1F5. So this is the number, equivalent number in hexadecimal, 1F5. Any questions here? Any confusion? No? Okay, so if not, okay, let's not do it as an exercise. Let me explain it and then we will have exercise in upcoming slides. So let's say we want to convert number 29B, which is an hexadecimal form, to equivalent binary. So what we do again here is the reverse of what we did in the previous example, that we replace each digit in the hexadecimal domain or in hexadecimal system with corresponding binary. So what is B? You can basically look from here. B is 11. So here you write the binary of 11. So how I know? Just by experience, but if you want to, you can convert it to decimal and you will see it is 11. How? Because the weight of the first one is, sorry, can I not control Z? Okay. Okay, so the weight of first one is 1. The next weight is 2. The next weight is 4. And the next weight is 8. But the binary symbol for weight of 4 is 0, so I simply ignore it. So I get 8 plus 2 plus 1. So 8 plus 2 plus 1 is 11, right? So 11 in hexadecimal is what? It is B, right? So what I can do is that simply I can replace the B with the binary of the 11, right? So it will become 1011. Then for 9, I can simply write the binary of 9, which is 1001. Again, you can either use the weights if I like you are comfortable with that. If not, you can do the repeated division on 9, repeated division with 2, and then you will forget the 4-bit value of 1001. And for 2, you can also, again, you can either, you can look at the weights, or you can do the repeated division and you will get the 4-bit value of 0010. And when you will put all of them together, you will get this binary number. And we can ignore these leading zeros because they don't have any value here. So we can have 101, 0011, 1011. Okay. Any questions? Please let me know if something is not clear. Everyone is so silent. I am not getting any response, but I hope that is a positive thing, which means like you are understanding everything clearly. But if not, let me know. Okay. So how can we convert from decimal to hexadecimal? Again, uh, like there are multiple ways. Let first talk about the second option because we have used this approach earlier. So one option is that you can convert directly from decimal to hexadecimal by repeated division. So what does it mean? So it means like, let's say if you have a number 275 and you want to convert it to hexadecimal. No, sorry, 275 is already in. Why can't I undo it? Uh, Let me check if. Okay, I will check that offline. But let's say we have a number 629 and we want to convert it into hexadecimal. So what we will do is that we will do the repeated division. And repeated division mean like let's say I have 629. Let me check. So I can simply divide it with 16. So if I divide 629 by 16, then I have quotient of 39, right? And the remainder of no, sorry. No, no, no. I wish I can. Let me do it on OneNote so that uh, here. So you can see 60, you can see my OneNote screen or not? Can anyone confirm, please?
Yes.
Okay. Okay. So we have 629, right? And if I divide 629 by 16. So I get quotient of 39, and I'm writing here remainder, which is 5, right? And then I divide again 39, which is quotient, with 39, so with 16, so I get 16 2 times 32, and the remainder is 7, right? And now if I divide again quotient with 16, so I get 0 as quotient and 2 as remainder. So now I do the same thing as I explained earlier, that I simply write the symbols from bottom to the top, so I get 275, right? So this is your number equivalent to 629 in hexadecimal form, right? Okay, so there is some, okay. Okay, let's go back to the, let's go back to the lecture slides. Yeah, so the first option is that you can do the repeated division just like I have shown you, like from 629, how you can convert it to 275. And the second option is, which is like kind of more convoluted, not straightforward, is like if you want to convert from decimal to hexadecimal, so you can convert the decimal number first to the binary form, and then from binary form you can convert into the hex. But I mean, I would not be more comfortable with this approach. So here is the doing the same example using the first option. So if you have number 629, so you are converting first into the binary using the weight approach instead of using the repeated division by 2. So here 629 is like, the weights are 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. After 512, it is 1024. The next weight is 1024, right? But 1024 is bigger than 629. So closest weight is 512. So then you subtract 512 from 69, and whatever is left, you look for a weight closer to it. And in the same, you keep doing so, and then you will, what will you do, that for all those weights which you have picked, you write 1, and for those which you haven't picked, you put 0. So I don't know if you guys want me to do this again for you or not, but like for example, I have picked the weight 512, so I write 1 for that here, right? Uh, so because 1024 is too big, so I picked 512 and write a 1 for this one, and then I subtract 512 from 6 to 9, so I get 117. So I look up for a weight which is uh, not greater than 117 but closer to 117. Smallest weight, like, which is not greater than the 117. So 128 is too big, so next one is 64, right? So I select 64 and write 1 for it, and then I subtract simply 64 from 117, so I'm left with 53. So then the smallest code, which is closer to the 53, is 32. And I keep doing so. I don't think you want me to complete it. If you want me to complete this process, then let me know. Otherwise, I'm assuming that you have already understood how the things are working here, right? So in this way, I will be converting it to the binary. And once I have converted into binary, then what I will do is simply I will group the bits, binary numbers, binary digits, which are also known as bits, in a group of 4. So I write these 4 bits together as 0101, and then convert them into the equivalent hexadecimal. So equivalent hexadecimal of 0101 is 5. Then I group the next 4 bits, these 4 bits together, and replace them with their equivalent hexadecimal value, which is 7. And then for next 4 bits, I am left only with 1 0, so I can append 2 zeros, so it will become 0010, and I will replace it with its equivalent hexadecimal, which is 2. So the number in hexadecimal will be 275, right? Any questions? Okay, so let's have a look at conversion from decimal to hex by repeated division. Uh, Actually, we have already done it in the previous. I have shown it on the how to do it on the on OneNote, so I'm not going to repeat the same slide, but you get the idea, right? So simply we will get 275 again. Okay, now I want you to do this exercise, uh, which is basically to convert the decimal number 94 to hexadecimal by repeated division. And I can give you like 2 minutes to complete this one. And when you are done, please let me know. Yeah. Okay. Uh, Regarding okay, before while I started doing the previous example, so I stopped the recording. So we missed a couple of minutes, but other than that, everything is recorded. And once the lecture is over, I will upload the link to the lecture recording in Canvas page. Okay. Just like I think I have provided the link for the first lecture on the Canvas page. Did I answer your question? I guess yes. If not, let me know. Okay. Okay, second option is that if you want to convert from hex to decimal, you can convert directly using the weights of hexadecimal system. So how? So again, if we have same number, let's say 6b2, and I directly want to convert it, so I will simply multiply all the digits with increasing power of 16. So here 16 raised to power 0, 16 raised to power 1, 16 raised to power 2. So the first digit is 2. So here I have 2. The second digit is B. But remember that B in hexadecimal is equivalent to 11 in decimal. So that's why I'm writing here 11. Okay. And then I have 16. And then I take sum of the products. And when I will take sum of product, it will be the same thing. Same thing 1714. Okay. To me, this is more easy. I mean, I don't know. I'm not saying that if I'm comfortable with one thing, you must prefer it over the other approach. But I'm just telling you that which one of them works more comfortably for me. Okay. Any questions until this point? Because after this point, we are not going to talk about conversions from one number system to another number system. So if you have a question, please let me know. Okay, two's complement. Let's first talk about what is two's complement, and then in the next slide we will talk about why we need the two's complement, right? So let's say if I want to calculate the two's complement of a binary number, so how can I calculate it, or how can I find it? To find the two's complement of a binary number, first I will find its ones complement. And how I find the ones complement? So I find the ones complement by replacing every zero by one and every one by zero in the number which is I'm trying to convert, for which I'm trying to find the ones complement. So for example, let's say you have binary number 0110 and you want to find its ones complement. So you will simply toggle the bit values. So if it is 0, you will replace it by 1, and if it is 1, you will replace it by 0. So if you have number 0110, so it will become 1001. Simple, right? Now this was one's complement. Now how we find the two's complement? You find the two's complement by adding 1 to the one's complement, right? So here is like how we can calculate the two's complement of 0110 by adding 1 to its one's complement. And when we add 1, so what it will become? So actually, I don't know how, if you guys know how binary addition works or not, but let me simply explain it. It is basically the same as addition in the decimal system. So if you are so this is one's complement, I am adding 1 to it. So here all the leading digits are 0, right? So if I add 1 to 1, it is just like uh, if I add 1 to 1, it becomes 2, right? And the binary in 2 is 0, 1. So I write 0 here, and when 1 goes to the carry, 1 is carried into the next position. So now I've add 1 0 0, so it becomes 1 here, 0 here, and 1 here, right? So this is your two's complement. So basically how you calculate find the ones two's complement, just first find the ones complement and then add one to it, right? So any questions at this point? No? Okay. Now why the question is why we need the two's complement. We need the two's complement to represent the sign number in digital hardware. Let me explain. So let's say if you have number 7 in decimal system and you have another number, so what will be its equivalent binary? It's equal 4-bit binary, let's say. Its equivalent binary will be 0, 1, 1, 1, right? Now, what about -7? How can I represent -7 in binary form? So, because minus is just a symbol for human understanding, right? So, computers cannot understand, just like the computers or digital hardware cannot understand the symbol 7, uh, the same hardware can also not understand the minus symbol, right? So, we need to find a way to represent the sign numbers, right? Only by using zeros and ones, nothing else, right? And two complement help us to do that. How? Let us try to understand in next slide. Okay. So let's say we want to represent a negative number x. So we can represent the negative, let's say for example, just like -7. So what I can do is that I can represent -7 by finding two's complement of 7. So if you want to represent a negative number x, so you will simply represent it by two's complement of magnitude of x, irrespective of its number, right? And if you add x and minus x in binary form, they must add up to 0. Now let's try to understand. Let's say we have -5 in decimal form and we want to represent it in binary form, right? So how can we represent it in binary form? So what we will do is that we'll first find the two's complement of uh, magnitude of 5, right? So you have like magnitude of 5, -5 is 5, right? So first you get the binary of 5. So the binary of 5 is 0 1 0 1, right? And then you take its two's complete one's complement. When you will do one's complement, it will become 1 0 1 0. All the bits are toggled here, right? And after that you add 1 to it. So when you add 1 to it, will become 1 0 0 1, right? Now remember that uh, if we are representing numbers uh, using binary form, then the positive number will always have a leading 0, and the negative number will always have leading 1. So if the most significant bit is 1, then it's mean that this number is negative. When we will convert it into the decimal, we will find that it has a negative value. And if the leading value or the most significant bit is 0, then that number is positive. So how we how we can convert, I will talk about it in the upcoming slide. But this is in this slide we are basically talking about how we can convert a signed decimal number to the equivalent binary form. For that, the procedure is that you first get only the binary of its magnitude, for example 5, which is 0 1 0 1. Then you get its ones complement, then you add 1 to it, and whatever result you get is the binary form of that negative number. So 1011 is binary form of -5. Okay. And most significant bit, if it is 0, then it tells us that the number is positive. If it is negative 1, then it tells us the number is negative, right? And that's why the most significant bit is called the sign bit, because it tells us about positivity or negativity of the number, right? Now, uh, before us, okay, any questions until this point? No? Okay, so ignore this next bullet point, ignore this one, okay? And try to answer my following question. If you have 2 bits, so what is the range of the values which you can range of the values in decimal which you can represent using 2 bits? Anyone, if you can answer any, you can put in the chat box if you know the answer. If I have two bits only, let me like maybe write here B0 and B1. What is the range of the values which I can represent using these two bits? Okay, if there is okay, -2. No, no, I'm not talking about signed numbers. Someone answered, Jaden answered that it is from -2 to 2. I'm not talking about, let's say that we are not considering the negative numbers. We are considering only positive numbers. Yeah, zero, yeah, zero to 3 actually. Because if you have two bits, then you can have four combination of bit values: 0, 0, 0, 1, 1, 0, and 1, 1, right? So this is 0, this is 1, this is 2, and this is 3. So you have 0 to 3, right? So it basically means that if you have two bits, you can represent how many different values? Four different values, right? So if you have two bits, so it is basically 2 raised to power 2. So you can represent four different bits, four different values using two bits. Similarly, if I ask you that if you have three bits, how many different values you can represent? So it will be definitely 2 raised power 3, which is equal to 8. So you can represent 8 different values. But the range of the values will be just like in case of 2 bits, it was from 0 to 3. So here it will be from 0 to 7, one less than the maximum 2 raised power 3. So basically from 0 to 2 raised power 3 minus 1. Everyone with me on that? Does everyone get the idea? Is there anyone who doesn't understand what I'm talking about? Okay, Victor, I'm considering yes as like you understand it, right? You have no problem with understanding what I'm saying. Okay, okay. So now we were talking about only positive numbers, right? However, if we say that we are using the given number of bits to represent not only positive numbers but also the negative numbers, then we will have a different story. Again, let me do the same thing. Like let's say I have a same, let's come back to this one. So remember we said if most significant bit is 0, then the number is positive. If most significant bit is 1, then the number is negative. Now if again focus on this one, right? So we have four different combinations. In two combinations, we have most significant bit as 0. And in the remaining two combinations, we have most significant bit as 1, right? So again, we have four different numbers, but then this is 0, this is 1, and this is -1, and uh, sorry, this is -2 and this is -1, right? I don't know. I mean, I wish I can write it. Let me try again the notepad. I Let me know if I'm writing on notepad, but if you cannot see, let me know. Okay. So we said that we have two bits, B0 and B1, right? And this time we are considering the signed numbers, right? So what four combinations possibly I can have for these bit values: 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. Since we said that we are considering the signed numbers, then most significant bit, which is bit 1, it will be considered as a signed bit, most significant bit, right? And remember, we said if most significant bit is 0, then number is positive. If 1, then number is negative. So it means that these two numbers are positive and these two numbers are negatives, right? So this represents 0, this represents 1, and this represents -2. Sorry, not -2. This represents -1 and this represents -2. So the range will be here from 0 to, I mean, on the negative side, you will have -2, and on the positive side, you will have 1, right? And this is basically equal to 2 raised to power n minus 1, and this is equal to, uh, we can do the math on the slides. So it will be like the range will be from the range will be 2 raised power n minus 1 minus 1 2, and the lower side with the lower side of the range of the lower range will be negative 2 raised to power n minus 1. Okay, so it will become equal to, in our case, like if you are using only 2 bits, it will be -2 to 1, right? So if, for example, you have n bits in total, the range will be from -128 to 127. You can simply plug in here n, value of n, which is 8, and you will get the range, right? But this is the range for the case when we are talking about the signed numbers. But if you are talking about unsigned numbers, where we are assuming that all the binaries represent only positive numbers, then your range will be from 0 to 2 raised power n minus 1. Any questions? Just like we saw that 2 bits can represent number from 0 to 3. Okay, any questions at this point? No? Okay, let's stop here, and next time we will talk about how we can convert numbers, binary numbers, which represent uh, two's complement binary numbers into equal and decimal form, right? So basically, how can we convert the signed binary numbers into equal and decimal form, right? Like positive signed numbers will convert into positive decimal forms, and decimal numbers, and negative signed numbers, binary numbers, will convert into the negative decimal numbers, right? So we'll talk about that in the next lecture. Any questions here? Any comments? We have like last minute. No? If no questions, then okay. For today, you guys have lab, right? I will be available online in the lab. You will have TA in the lab also. I will be available on Zoom. And yeah, if you have any questions, ask TAs, or if you want, you can ask me on the Zoom. The Zoom link is available for lab on the Canvas page. Okay. So good luck with the lab, and then see you uh, in 4 or 5 hours. Bye for now.